Hello and welcome to MetaMath. In today's video, I'm going to be covering modular arithmetic and number theory. So to start off with here, I've drawn a clock to help illustrate how modular arithmetic works with a fairly common example. As you can see, it's 2 o'clock, and if I was to ask you what time it would be in 5 hours, you would probably tell me it was 7 o'clock. And if I asked you what time it would be in 10 hours, you would tell me 12 o'clock. But if I asked you what time it would be in 14 hours, you would still probably tell me the correct answer, which is 4 o'clock. But the difference here being that unlike 7 o'clock where we just added 5, or 12 where we just added 10, we can't simply just add 14 to 2 to get 4, because otherwise we would end up with 16. And while we can't count directly off the clock and go in a circle, it helps to think, how come 4 and 16 end up in the same spot anyways? And the answer is with modular arithmetic, because 12 is the cycle of a clock, essentially. Time is always between 1 and 12. We never go outside of these numbers, and that's why in a 24-hour period, there's 2 12-hour cycles, and the numbers between 1 and 12 are always the ones we use. So I'm going to introduce a little bit of notation when it comes to modular arithmetic, and I don't want to get bogged down in the terminology here, but this modular arithmetic is a system for arithmetic based on cycles of remainders, and I touched upon that a little earlier. And like the clock, a cycle of remainders is just remainders when divided by a number. So here we have an example of modular arithmetic. A is congruent to b mod n is how we would say this. So n in this example is the modulus of our system, and a modulus essentially is the number we are dividing by. It's the number we want, or we take the remainders divided from. So 12 was our modulus earlier because we are dividing numbers by 12 to get the remainder. So 4 is a remainder automatically because it's less than 12, but 16 produces a remainder of 4 when divided by 12. So we would say that 4 and 16 are congruent in mod 12 at least. So we don't have to necessarily write A and B being equivalent as a statement. We can simply just write 4 mod 12, or we could write 16 mod 12, and those would be expressions. So now we also have residues, and a residue is a number that is less than or equal to, is strictly less than n, but is greater than or equal to 0. So in the clock, our residues are between 1 and 11, and while we don't have 0, 12 is essentially in the same spot as 0. And the easiest way to think about this is these are all the unique values you can get when you divide a number by the modulus. So when we divide any number by the modulus, its possible values lie between 0 and 11. If we got 13, for example, that would just be the same thing as 1 because we can still go into it. 16 is greater than 12, so we can take a remainder and get to 4. We can't go any smaller than this, but if we go larger than 11, we can go to 0. And as a result, we have a cycle, and that's really how modular arithmetic works. Think of it as a cycle. So we also say a residue class consists of all numbers congruent to that residue mod n. So for example, 4 and 16 form a residue class, and we can go on and on and on. So for example, we could have 28, we could have 40, essentially all multiples of the mod plus that residue, plus or minus that residue, give us our residue classes. So I'm going to introduce now another example here so we can get familiar with how mod actually works. 3 is equivalent to 8 mod 5. So what this is saying again is that 3 has the same remainder as 8 when divided by 5. And this is apparent because 3 itself is less than 5, and 8 is 3 more than 5, so it'll leave a remainder of 3 when divided by 5. And if we look at a number line here, we start with 0, go to 1, 2, 3, 4, 5, 6, 7, 8. We start off with all the residues, 1, 2, 3, and 4. We notice that once we hit our mod, we loop right back from the residues and we start numbering them all over again. And from this number line, we can see that 3 and 8 do have the same remainder, and as a result, they are congruent mod 5. And this would extend in both directions. We could go easily the other way, -1, -2, and we would see that they would still be equivalent because they have a distance of 5 apart from each other. So all numbers that have the remainder of 3 will be congruent mod 5. So with this, we can move on to its properties, and it may be a little bit different, but for the most part, modular arithmetic is fairly similar to traditional arithmetic, especially in addition, subtraction, multiplication, exponentiation. So let's assume that we have a and b for some a and b equivalent mod n, and c and d equivalent for some mod n. So we can then deduce that a plus c is equivalent to b plus d mod n. And I'll provide an example here real quick. If we have 3 is equivalent to 8 mod 5, and we have 1 is equivalent to 6 mod 5, if we add these two statements together, we produce another equivalent statement. 4 is congruent to 14 mod 5. And to easily check this, just add 5 twice to 4 and you end up with 14. So another example we could use with this is to find the units digit of a sum. So if I asked you to find the units digit of 293 plus 471 plus 3 plus 16 plus 12, this is a fairly large sum and it would take a while to calculate this, but if I asked you to find the units digit, we don't even have to worry about most of these digits. The units digit allows us to take this entire sum, but in mod 10. So in mod 10, we just take the remainders of everything, and the remainders of a number, when divided by 10, is simply its units digit. So all we have to do now is add the units digit of these numbers. And we have to find the sum now. 3 plus 1 plus 3 plus 6 plus 2, plus 2, all in mod 10. And now we can do this fairly quickly. 3 plus 1 is 4, plus 3 is 7. 7 plus 6 is 13. 13 plus 2 is 15, which is equivalent to 5 mod 10. So we end up with the units digit of 5 because 15 is not a possible digit, so we have to find the next value that works. And likewise, multiplication also holds true in modular arithmetic fairly similarly. So if we had 3 equivalent to 8 mod 5 again, and we had 2 equivalent to 7 mod 5, we can multiply these two things and get 6 is equivalent to 56 mod 5. And if you look at the difference here again, we have a difference of 50, which is a multiple of 5, so this statement is correct. We could also approach it in another example where we take the units digit. So if I have the product, let's say 47 times 29 times 13 times 16 times 7, the product of this would again be a really large number. But if I was just to find the units digit, we could take this entire thing and use mod to simplify it. So taking the mod again, we don't have to worry about any of the other numbers. We just want the units digit. And if we're just worrying about the units digit, we don't have to worry about the actual numbers themselves. So we can just find the product of 7 times 9 times 3 times 6 times 7. Now what we can do here is, rather than having to multiply all of these large numbers out, we can notice that 7 and 7 can each be written as -3. So we have -3 times -3. 9 is a -1. And 3 times 6 is what's left from the positive numbers. So we have -3 times -3 gives us 9 times -1 times 18 right here. So we end up with -9 times 18, and this ends up being a 1. -9 plus 10 gives us 1. So -9 is congruent to 1 mod 10, and we can just write it as 1 times 18, which is 8 mod 10. So we end up with the units digit of 8 in our product. And lastly, exponentiation, which is again just repeated multiplication, also holds true here. So if we had 3 equivalent to 8 mod 5, if we raise both sides to the second power, we get 9 equivalent to 64 mod 5. So the difference here is 55, which again is a multiple of 5, and we can see this holds true fairly easily. Now, let's say I asked you to find the last digit of 3 to the 204th power. How would we go about solving this? Well, let's start by just writing out a sequence of 3's. We start with 3 to the first, which is 3. 3 squared. 3 squared gives us 9. 3 cubed gives 27. And 3 to the fourth gives 81. 3 to the fifth equals 243. And among all of these, we notice a pattern start to form. 3, 9, 7, 1, and then we repeat back to a 3. And this indicates that if there's a cycle, we might want to use modular arithmetic. So our cycle is 4. So we want to evaluate the exponents here, mod 4. So we want to find what 204 mod 4 is, so we can check where it belongs on this cycle. So 204 mod 4 is going to be 0, which is equivalent to 4 because it's a perfect multiple of 4. So our units digit is going to be 1. So this has a units digit of 1. So with that, I hope this tutorial or introduction to modular arithmetic helped you. In the next video, I'm going to be covering more applications and more uses of modular arithmetic. Make sure to subscribe and like if this video helped. And if you have any questions, please leave them in the comments below. Thanks.